session on social network analytics and fraud analytics for the University of Nottingham, Malaysia campus, if I'm correct. So my name is Bart Basis. Indeed, you can find my email address here in case you want the slides afterwards. I'm sure Yvonne will send them around. But in case you have any questions or have any references you'd be interested in, you can always send me an email. So the question is, how did I get here before I started working on the slides of this presentation? And how I got here was when I finished my PhD at the Catholic University in Leuven, which was in 2003. One of the members of my PhD committee was Professor Lynn Thomas. And at that time, Professor Lynn Thomas, he's one of the big names in credit scoring, who unfortunately is no longer with us. But he was a professor at the University of Southampton. And at the end of my PhD, he invited me to move to Southampton, where he was supervising actually some very bright PhD students at that time. And one of them was Yvonne, right? She was one of Lynn's PhD students. And that's how I got into touch with Yvonne. And here you can see some pictures of us back at the time when we were even more good looking than we are today.
Right.
So I'm
No,
yes.
I think your slide is not moving and you're frozen.
You're not moving and frozen,
Yeah,
right? You can see it now?
Yeah. Okay.
Okay.
Now, yeah. Oh yeah.
Excellent. So here
Thanks
you
for
can
that,
see
Bart.
you can see the pictures, right? Okay, you can see
Yes, we
pictures.
can see the
Okay,
pictures.
excellent. So here you can see, as I said, here you can see some of the pictures back in the old days when, as I said, when we were still even more good looking than we are today, right? That's me and Yvonne. I'm sure you recognize us sitting at various conferences, spending some fun time together. And we stayed in touch throughout these many years. And that's how I ended up doing this presentation here for the University of Nottingham in Malaysia campus. Here you can see some more information about myself. I just moved slides, Yvonne. Can you see it?
Yep.
Yep, excellent. So as Yvonne said, I'm a professor of data science and analytics at the Catholic University of Leuven in Belgium. Leuven is known for a couple of things. It's known for having the best university of the country and far beyond. We have a very old university. It was founded in 1425. And Leuven is also known for something else that Belgium is actually known for, and that's beer. And actually, we have one of the big breweries, which is called AB InBev, which is about, I mean, from where I'm sitting right now, it's about 300 yards as the crow flies, or 300 meters. I don't know what you guys use, yards or meters. So, I mean, actually, when I sometimes get into the office in the morning, I can smell the yeast of the beer brewing process, which is actually a very nice way to kick off your day, right? So, I'm a professor at the Catholic University of Leuven in Belgium. I also maintained my connection with Southampton. Where Yvonne also did her PhD studies. As you may know, I'm still a part-time guest lecturer at the University of Southampton, and my research is big data analytics. I have a research team right now of about, I think, 6 PhD students that all work on topics related to analytics, ranging from credit risk to fraud risk to customer lifetime value modeling. And if you like to stay in touch with my research, you can connect with me on any of my social media accounts. You can try and connect on LinkedIn, but unfortunately, I'm at my LinkedIn limit, so I always need to kick out some less interesting people before I can accept new ones. So that may take a while before I do that, but feel free to connect on YouTube, on Facebook, or on Twitter. Just send me an invitation. I'm more than happy to connect. I've written various books on the topic of credit risk modeling, ranging on the topic of analytics, ranging from credit risk to web scraping, fraud analytics, model risk, profit-driven business analytics, and so on. And the book, which is probably most relevant for the topic that we're dealing with today, is this one on fraud analytics, right? So this is the one that I think is most relevant because it covers both social networks and obviously the very important topic of fraud detection. As Yvonne rightfully mentioned, I also have my own online learning platform, bluecourses.com, which features several online learning courses. Those courses are self-paced and pre-recorded. That means that they consist of a set of videos that you can watch at your own pace. Typically, they have about 4 to 6 hours of videos each, with Python and R scripts blended in between, quizzes blended in between, and at the end of the course, you can also get a certificate, which you can proudly post to your LinkedIn accounts in case you would be interested. Okay, so that was the intro. What I'm going to talk about today is I'm going to talk about social network applications. Then we're going to talk about basic concepts of social networks. And then we're going to talk about defining a social network and how we can use it for predictive analytics, how we can use it to make predictions. And in order to make predictions with social networks, you have to featurize them. Many analytics nowadays is still being conducted on tabular data sets. So a tabular data set is a data set in which you have rows that represent customers, that represent companies, that represent maybe bank accounts, and columns which represent predictors. And one of the columns is a special type of column, typically, is the target column. The target column or the target variable, which could be a fraud indicator, indicating whether a person, whether a corporate, whether a bank account, or whether any type of transaction is considered to be fraudulent, yes or no. This is what we refer to as supervised learning or predictive analytics. So one of the key challenges when you have social networks is to move from that network to a tabular data format. In other words, what we're going to do is we're going to do feature engineering. We're going to derive features from the social network that we can summarize into columns of our tabular data structure. And we will do that by discussing centrality measures. We will do that by discussing community mining. We will do that by discussing homophily and social network-based predictive analytics. So that's the outline of the presentation. If you have any questions, maybe write them down, and at the end of the presentation, we will have enough time to answer any of your questions that you may have. Now, when I say social network applications, many of you will probably think about Facebook, about Twitter, about Google+, about LinkedIn, about maybe TikTok, Instagram, etc. And though these are also examples of social networks, they're more what I would refer to as social media. And when I think about social networks, I'm taking a much broader definition of a social network. It could be any type of network of entities which are connected in a particular way. So a social network has nodes and has edges. The nodes can be people and the edges could be any type of edge, not a Facebook or LinkedIn connection, but the edge could also represent somebody calling somebody else. So just a call. So I could look at a call graph, for example, where one person calls another graph. Likewise, in an academic setting, I can look at people that cite other people or authors that cite other authors. So here the nodes are authors of academic papers and the edges are citations. I can also look in an email setting, for example, at people sending emails to each other. Here the nodes are people and here the links are emails. So social networks are a lot more broader than merely Facebook, LinkedIn, Twitter, etc. For example, they could be people, the edges could represent emails being sent between them. They could be people, the edges could represent phone calls being made. They could be companies, the edges could represent shared resources like employees, infrastructure, equipment, shared addresses, etc. They could also be websites, and the edges could be hyperlinks. They could be researchers, and the edges could be co-authorship or citation. So the thing I want to convey with the slides is that social networks are a lot more than social media, right? So when I say social networks, do not only think about social media, but think about any type of business application or business setting where you have nodes and edges defined in a particular way. I'm going to give you one example of a social network application, right? Um, Yvonne, can you see the movie now? I'm showing a movie. Can you see that? Okay. So you see a graph. This is a real life data, right? And what you basically see now is you see 4 blue nodes. This is a graph which we've taken from real life telco data. And what are the nodes? The nodes are people like me, Yvonne, Tom, and Sarah, and the edges represent connections, calls, in other words. It's in a telco setting. So the edges represent one node that made a call to another node. So what we'll see now is that the network grows a bit in time. We will see more and more blue nodes being added to the network and calls being made. the network evolves gradually in time, right? So let's just play this movie. So we've played further. You see more nodes, right? So you see all blue nodes. These are all people. Edges represent calls. So let's go further. This is all networks. This is a subset. And what we see right now is we see a first red node. And the red node depicts a person that is churning. Churning means that this person is no longer happy with the service that was offered by the telco provider, because the telco provider is expensive, because the telco provider provides bad coverage in certain types of regions in the country, etc. So a red node means that a person is journeying from telco provider A to telco provider B, right? And that's not what telco provider A wants, right? Telco provider A does not want any of the red nodes. Let's see what happens right now as this graph, as this network evolves in time. We see another red node. We see other people churning. You see that? And we see more churning. People leave. Obviously, people also are being added to the network as new customers come in. And let's see how this network further evolves in time. Get more churners, you get more churners. These two churners right here are very close to one another at the top. You see two churners that are very close at the top of the network. Probably one influenced the other. Not sure, could be a mere coincidence, but could be that they influenced one another. Let's see how the graph evolves further. We have more churners that pop up, more churners, more people leaving. And what you see at a certain point is that you will see churners that are situated very close to one another, right? Have a look at these three churners right here in the middle of the graph. You see clusters of churners, most likely because one influenced the other. And let's have a further look, right? Look at that chain. Isn't that a beautiful chain? Perfectly depicting the viral effect of churn. Perfectly depicting that most likely one person initiated the churning of his or her neighbors. And instead of losing one customer, the telco provider lost a whole bunch of customers. I would have to count them, maybe around 10. And that perfectly depicts the viral effect of churn. And it's precisely this effect that we will try to capture using social network analytics. Obviously, we do not only have it in churn, right? We do not only have it in churn where we start from call detail records, as you see right here. Call detail record means that you start from a text file, a log file that depicts who calls who, what number calls what number, what's the start of the call, what's the end of the call. Based upon these call detail records, you can construct a network as you see right here, and then you can try and predict the red nodes which represent the churners. We can do more than just using it for telco. The title of this talk is Social Networks for Fraud Detection. And that's why we also see social networks often popping up in a fraud detection setting. Yvonne, just checking, you see my slides again, right?
Yep.
Yeah, excellent. So in fraud detection, fraudsters often tend to cluster together. Sometimes they even exchange knowledge how to commit fraud, a practice which is commonly referred to as collusion, right? Whereby multiple fraudsters get together and think about very creative ways of setting up fraudulent schemes. Fraudsters often tend to use the same resources, like fraudulent credit card holders can try and use the same merchants to process fraudulent transactions. So it's often related to the same event or activities. Common examples of where social networks could play a very big role in fraud detection are credit card transaction fraud, tax evasion or social security fraud, and identity theft. And in my research, I've worked on both credit card transaction fraud and tax evasion or social security fraud. So let's get into a little bit more detail in that. This is a screenshot which I took from a paper that I've written with one of my former PhD students, Veronique van Vlaselaar, who now works at SAS, which is a big commercial software vendor that also has an office in Kuala Lumpur. And long time ago, I've been also teaching courses in KL. And here you can see a network depicted. This is again an extract from real life data, whereby the yellow edges represent stolen credit cards, right? The blue edges represent stores or merchants that process credit card transactions, which are either legitimate or fraudulent. So the red edges represent fraudulent transactions. the green edges represent legitimate transactions. What you will typically see is that there are merchants that process quite a lot of fraudulent credit card transactions, but obviously every now and then they will also process legitimate transactions to cover up or hide their fraudulent activities. So in other words, this gives a lot of potential and opportunity for predictive analytics to define these networks and then to featurize them into columns or into predictors in your predictive modeling data set. Here you can see it in tax evasion. Belgians are very creative in various ways, unfortunately also when it comes to tax evasion. And here you can see what we call a spider construction, which is actually not only a Belgian thing, but kind of international tactic or technique to do tax avoidance. And what you have is that you have the central node, which is the key perpetrator of the fraud. This is a company. The central black node is the malicious company that sets up the whole fraudulent practice. And what this company does is it starts up a new company, which is like this white node right here to the left. And this company has some physical resources, it has some equipment, some infrastructure, there's some people working in there, and it's not paying its taxes. It's not paying its social security taxes or any kind of general taxes. So the firm intentionally goes bankrupt because it's not paying its taxes. Note that bankruptcies, in fact, can be due to two different reasons. A bankruptcy can be due to financial insolvency, but it could also be part of a fraudulent structure, of a fraudulent mechanism, right? In this case, I'm not referring to financial insolvency, but I'm referring to intentionally not paying taxes or social security contributions so as to intentionally go bankrupt, which is fraud, which is actually not the real bankruptcy, but is fraud. So this guy to the left goes bankrupt, and what then happens is that the key perpetrator of the fraud moves all the assets, so the people, the infrastructure, the machinery, to a new company, which is again doing the same thing. It's not paying its taxes, not paying its social security contributions, it's going bankrupt. And it keeps on doing that. So we have a series of bankruptcies that are all connected to one another that make up a social network whereby assets, people, infrastructure, machines, etc., are moved all the time, which means that we can try and model this as a social network and then leverage this for predictive analytics and see whether we can get some predictive strength out in order to better detect these fraudulent spider constructions. This is what we have successfully done, for example, in collaboration with the Belgian government. So here you can already see the benefits of using social networks, not only for credit card, but also for fraud detection. It also applies to identity theft, right? Let's say that this is to the left, we have the regular situation whereby a person makes calls, for example. Let's say that this person in the center right here, one is Yvonne, that makes calls to her parents, families, colleagues, friends, etc. And all of a sudden, I steal Yvonne's identity without her knowing it. So I'm customer two right here. I'm the malicious guy. Yvonne is the good guy. A bit hard to imagine. I would assume, but anyway, let's assume this. So what happens is I take Yvonne's identity, and what you now see at some point is that the phone identity that's related to Yvonne starts making calls to my friends, starts making calls to customer two or Bart's friends. So you see that because of the fact that customer two me stole Yvonne's identity or customer one's identity, you see that customer one or Yvonne starts making calls to friends of Bart because it's Bart that stole Yvonne's identity. So this is another way that we can try and construct these networks to look for suspicious patterns of identity theft. So part I want to convey with these three examples on credit card, tax avoidance, and identity theft is the potential of social networks to detect fraud. But how should we put this all into action? How are we going to materialize this? Well, the way we will materialize this is first we have to think about what are the nodes in the network, right? What are the nodes? The nodes could be the customers, could be households, could be credit cards, could be bank accounts, could be patients, and so on. So all of that very much depends upon the business setting we're in. Once we have defined the nodes, we have to think about the edges. How are we going to connect them? The connection could be a call, which is made from customer A to customer D. The connection could be a money transfer from bank account A to bank account D. The connection could be a citation in an academic setting whereby authors cite each other. The connection could be anything. And that's part of your business problem. That's part of your business setting. And that's also part of your creativity as a data science. You're taking this course, you're taking this session as part of a data science related course. And as data scientists, we have to be very creative. That's one of our core properties. And it also comes down when we define those social networks. It all boils down to creativity in order to define a network in terms of the nodes and the edges. The edges can also be weighted, like A to D, customers. A and D call each other 8 times a week. D and C call each other 2 times a week. A and C call each other 4 times a week. So A and D are more closely connected than D and C because they call each other a lot more weekly than D and C, right? You can take into account weights. Depending upon the setting, you can also take into account the direction of the relationship, where you can make a distinction between incoming and outgoing calls. A calls D 8 times a week. D calls C 2 times a week. So that's also part of your network definition. And obviously, the links aggregate the intensity of the relationship between the two nodes and can also come in handy later on as we will start featurizing this network. So here you can see we typically start from transactional data from the two nodes, and then some data that can help us define the intensity of the edges, like the duration of the call, maybe even some geographical information that can come in handy, etc. And the way we represent social networks is then using a sociogram, which is visual, which is nice, but it doesn't scale very well. A sociogram, I mean, you can visually represent a network, but if you have millions or thousands or hundreds of thousands of nodes, you can no longer visually represent it. So you have to represent it in a mathematical way using an adjacency matrix, for example, right? So the columns in rows in the adjacency matrix represent the customers, and the matrix is then populated with zeros and ones to indicate whether there's a connection between them. Here you can see that A and B have a connection, 1. A and D have a connection, 1. 0 means no connection. This adjacency matrix here is a binary matrix. We just indicate whether there's a connection, yes or no. And obviously, it's also symmetric, right? In the sense that if there's a connection between A and B, there's also a connection between B and A. This adjacency matrix will typically be very sparse. And when we say very sparse, it's going to contain lots of zeros, right? So there's many people, there's a lot more people that don't call each other than there are people that do call each other. That means that this adjacency matrix will contain an abundance of zeros. So in order to represent it in a more compact, parsimonious way, we can represent it using an adjacency list where we only enumerate the connections that are there. This also doesn't take into account the weights. If we want to take into account the weights, it's no longer a binary matrix. It's a matrix that contains the intensity of the connection. Does not only contain the information, is there a connection, but also the intensity of the connection, right? So here you can see those weights being directly embedded in both the adjacency matrix and also the adjacency list. Okay, cool. Now, if you do statistics, right, and I give you a data set, like a credit scoring data set that you undoubtedly heard of, and I ask you, give me some exploratory statistics for each of the variables you have in your credit scoring data set, like age and income, etc. What you probably are going to do is you're going to give me the average, you're going to give me the median, you're going to give me the standard deviation, maybe the maximum, maybe the minimum, maybe some quartiles, etc. So these are what we call basic statistical summaries or representations of your data. And those also exist for networks. For networks, we can also have some basic statistical properties that represent how central every node is in a network. And we can look at the centrality of a node in the network from various perspectives. We can look at the degree of a node, we can look at the closeness, the betweenness, and the graph theoretic center. So let's zoom into each of these network centrality measures into a little bit more detail. But first, we have to define a concept which is called the geodesic. And the geodesic represents the shortest path between any two nodes in the network. So geodesic means shortest path between any two nodes. So if I would be looking for the geodesic between node A and node I in this network, you can see that this geodesic is depicted in blue. So the shortest path between node A and node I is to go from A to C, then from C to G, and then from G to I. Do note that geodesic need not be unique. There could be that between two nodes in the network, there are multiple geodesics possible, right? So there could be multiple shortest path between any two nodes, right? It could be unique, but there could be more than one shortest path between any two nodes. We will use this concept in a few seconds and a few minutes when I talk about betweenness. But first, let's talk about degree. Degree tells me the number of connections a node has, which is pretty obvious, right? For A has two edges, two connections. D has two connections. C has three connections, so degree is three. B has one connection. This is what we call the degree. We can normalize it, which means that we divide it by the number of nodes minus one. So here we have four nodes minus one, that's three. So we divide 2 divided by 3 is 0.66, right? That's what we call the normalized degree. So the degree is a first centrality measure of a node, but we can also look at um, the closeness of a node to all other nodes in the network. How close is a node to all other nodes in the network? Let's calculate that for node A, for example. So how close is node A to node D? Well, the distance between node A and node D is 1. So it's only one step away. So here we get the 1. This is this one. The distance between node A and node C is also 1. So this is my second one. And the distance between node A and B, so if I want to go to node B, I have to take 2 steps from node A to C and C to B. So that's 2. So 1 plus 2 gives me the farness. How far are all the other nodes from node A? If I take the inverse thereof, it gives me the closeness, which I can again normalize by the number of nodes in the network. So it gives me like the average distance of one node to the average distance or closeness of one node to all other nodes in the network. That's what we call the closeness, right? Every node has a closeness as you see right here. So here you can see that A is closest together with D to all other nodes, and no, B is closest to all other nodes in the network, okay? Then we can also look at the betweenness, and the betweenness counts the number of times that the node appears in the geodesic. So if I look at any two nodes, and the geodesic or shortest path passes through a particular node, then that is factored into the betweenness. So the betweenness looks at the betweenness for a node I, so node Ni, is computed as for all possible pairs of nodes, how many times is the shortest path between node J and node K passing through node Ni. So it counts, the betweenness for a particular node counts how many times the shortest path or geodesic between any two other nodes passes through that node. So if you have a very simple linear network right here, very simple network, A is connected to B, B is connected to C is connected to D, and D is connected to E. The betweenness for node A and E is 0 because there's no shortest path between any two possible nodes that you can think of that passes through node A and E. So A and E are both connected to each other. So the betweenness for node A and E is 0.
Right.
Okay, so you dropped out for a second. Can you hear me back?
We lost you for a second. Yeah.
Yeah. Yeah.
Yeah.
So you can hear me back. You see my slides back?
Yeah.
Excellent. Yeah, I don't know what happened. So I was. What was the last? The last thing you heard was the betweenness, right? I was explaining this slide, right?
Yeah.
Okay. So the betweenness counts how many times a node is situated on the geodesics or the shortest path between any two other nodes, right? So um, A is not on the shortest path, E is not on the shortest path between any two other nodes. B is between A and C, it's between A and D, it's between A and E, so it has a betweenness of 3, whereas C is at the center of this very simple social network, so it has the highest betweenness, right? Because it's between A and D, A and E, B and D, and B and E. So these are very interesting measures, especially the betweenness, because nodes with a high betweenness sit in between communities. So here you can see a big community to the left and a big community to the right, and the red node sits in between both of these communities. So the red node has the highest betweenness, right? So nodes with high betweenness separate communities is something that you should try to remember from this discussion, right? Then we have another descriptive statistic, which is sometimes used to characterize nodes in the network and particularly their centrality in the network, and that's the graph theoretic center. That's the node with the smallest maximum distance to all other nodes. So if I look here at this red node, the maximum distance to a node is 2, right? So all other nodes are within a reach of 2 steps. So that means that this, and since this is the smallest maximum distance to all other nodes, the red node is what we could refer to as the graph theoretic center. So these are all very interesting things to play around with if you have a social network, and that's the first way to characterize or featurize your social network. You still remember, if we featurize a social network, what we're actually doing is we're trying to build a network first and then try to summarize it into predictors, into variables that we can add to our tabular or our Excel data set and then use later on for prediction using logistic regression, using decision trees, random forests, etc. So here you can see a toy network, which is often used in the literature to illustrate things, where you have, it's called a kite network because it represents a kite that kids or sometimes even adults play with at the beach. And you can see that there's various types of things. We can look at the person that has the highest degree. And the person that has the highest degree, most of the connections, if I would ask you, I'm sure you would see that the person that has the highest degree is Diane, right? So she is considered to be a connector or hub because she connects a lot of different people. She connects Andre, Fernando, Gart, Beverly, Ed, and Carol. If you would actually calculate the closeness of every node, you would see that the the 2 people that are closest to everybody else, and hence are in a very suitable position to monitor the information flow in the network, then that would be Fernando and Gart. They have the highest closeness, so they're close to everybody else in the network and are in the best position to monitor the information flow in the network. If you would look at the person with the highest betweenness, you would see that this is Heather. Heather sits in between communities as she connects Ike and Jane, which is like a separated community, to this big community right here. So you can see that for the small toy network, this kite network, that the nodes with the highest degree is Diane is not the same as the 2 nodes with the highest closeness, which are Fernando and Gart, and not the same as Heather, which has the highest betweenness. You can see the numbers right here in case you would like to calculate it at home. Okay, now these centrality measures can be very usefully adopted to do, for example, community mining, to find communities in the network. And if you find a community in a network, a community is much like a cluster in classical descriptive analytics. If you do cluster analysis, like using k-means or hierarchical clustering, you want big within cluster similarity and big between cluster dissimilarity. You want members in a cluster to be as similar as possible to each other, and you want observations or customers from different clusters to be as dissimilar as possible. Same goes with community mining. If you do community mining in telco or fraud networks, you want members within a community to be highly connected. That's why they make up a community. And you want members between communities to be loosely connected. And that's why we can do community mining. Here you can see an example, for example, of a French play. It's a French play from Victor Hugo, um, where the notes are actors. The play is actually Les Miserables. It's a famous French play by Victor Hugo. The notes are characters, and an edge between two characters indicates that both characters appeared on stage together. There was a joint act of both characters together. And using this very simple toy network almost, we can do community mining to see what are the communities of characters that frequently occur together on stage. We can analyze that using a community mining technique, and the resulting communities are then depicted using colors. So you can see we have a yellow community, a green community, a red, a blue community, etc. So the communities are represented using colors. So, and that's very important in fraud analytics to find these communities, to find which are the nodes, which are the people, which are the companies that set up the fraudulent practices, because setting up a fraudulent practice is something that can be the result of peer pressure. Peer pressure can actually strengthen the tendency to commit fraud, where one person or a whole bunch of persons put pressure on a victim, for example, to be part of a fraudulent scheme. So are people more likely to commit fraud if they are influenced by a whole community than if they were influenced by only one fraudulent individual? I would say it's part of human nature, and I would say yes. Hence, community mining definitely has its potential within fraud detection. And one of the most famous algorithms to detect communities in fraud analytics is an algorithm which is called the Gervin Newman algorithm. And it works very similar to divisive hierarchical clustering. Divisive hierarchical clustering is a type of clustering whereby you start from one big cluster of all your observations and you kick out the ones that don't belong there, that are too heterogeneous, that are too dissimilar to the rest. That's how divisive hierarchical clustering works. So here the Gervin-Newman algorithm exactly works along the same lines, but it's calculating that graph centrality measure we referred to earlier on, the betweenness. The betweenness is a node that sits on the geodesics between a lot of other nodes. Hence, it connects communities. So the Gervin-Newman algorithm starts by calculating the betweenness of all existing edges. It then removes the edge with the highest betweenness because that's connecting two dissimilar communities. All the betweennesses of the remaining edges are recalculated, and it keeps on doing that until no edges remain, right? And basically what you have then, you can see this illustrated right here. We calculate the betweenness of all existing edges. We don't have the time to do it now, but if you would see very easily that the betweenness of this edge is the highest because it sits in between two different types of communities. So that's the first one that we're going to cut because it has a betweenness of 49. It results into these two communities. Then we recalculate the betweenness again. It results into these four red lines. These have the highest betweenness, so that gives us this community mining exercise until we reach the end where every node makes up its own community. So that's perfectly how the Gervin-Newman algorithm works as a divisive hierarchical clustering algorithm steered by the betweenness. And just we have in a classical clustering algorithm where you can use a scree plot that indicates the differences or the dissimilarities when each of the cluster cuts are being made, we can also have similar measures here to help us decide upon our optimal set of communities. One of these measures, which I don't have time to report on now, but if you're interested, more than happy to give you further background references, is the modularity Q measure. The modularity Q measure is a measure that helps us decide upon the optimal community mining solution. Because remember, we started from here, right? One big network, and then we cut it part by part into smaller parts until we arrived here. And the optimal community solution is situated somewhere in between. Here you can see this whole clustering exercise again neatly visualized. Okay, so at the end of the day, what we want to do is we want to do predictive analytics. You still remember that movie that I showed you where we had like customers that were calling each other, and that churn in that network, in that telco network, spread much like a virus in a medical setting, right? So it's like one customer is churning, and he or she is infecting other ones to churn as well. And basically, one of the underlying ideas there is the idea of homophily. And homophily is often referred to as birds of a feather flock together. Why do I like to hang out with my friends? Right? Why? What characterizes my friends? Well, I like to hang out with my friends because they also, I mean, because we have some joint interest, because we both like to watch soccer. Yesterday there was a very nice soccer game between Belgium and Germany, and we were very proud to beat Germany in Germany. So we won 2-3, which were very soccer is very big. So why do I like my friends? Because they like soccer, because they like good food, because they like to have a beer, etc. That's the concept of homophily. It means that there's some similarity between me and my friends. And birds of a feather flock together, or put differently, people have a tendency to associate with others whom they perceive as being similar. And it's exactly this homophily pattern that you can also find in social networks. The networks, the nodes, the connections indicate a connection between two nodes, indicate a certain type of homophily between the nodes, which can also extend to their behavior, which could also extend to their fraudulent behavior, to their churn behavior. It could imply that if two nodes are connected and one has been engaged into fraudulent activities, that the other one or other ones that are connected are also likely to be engaged in fraudulent activities. And it's precisely this phenomenon that we try to capture using social network analytics. Here you can see, for example, to illustrate homophily, you can see a graph that depicts the correlation in a call detail record setting, so in a telco setting, of the monthly caller income and the monthly callee income. You can see like there's some nice economic connection in terms of the caller and the callee being part of the same economic circle because their income is very similar according to this plot that was taken from this paper right here. And that's what we try to detect, actually, homophilic patterns within social networks. So fraudsters are more likely to be connected to other fraudsters, and legitimate people are more likely to be connected to other legitimate people. It will never be perfect. It's not like fraudsters are solely connected to fraudsters and legitimate people are solely connected to legitimate people. But if it's stronger than random, then it offers opportunity for us to leverage that for predictive analytics. That's really very important. So in fact, what you see right here, this is part of a real life network whereby the green companies represent legitimate companies and the red companies represent fraudulent companies. In fact, this is a screenshot which I have taken from a paper that we've written on tax evasion fraud. And if I would ask you, is there homophily in this network, yes or not, without quantifying it using statistics, which you can do, but just by merely visually inspecting this network, I'm sure you probably say yes, and you would be rightful to do so, because if you look at this graph, you see that tends to be a big concentration of the reds. The red companies tend to be highly interconnected. It's not perfect. There's connection with greens as well, but it will never be perfect, right? As long as it's stronger than random, we can leverage it for predictive analytics. And that's exactly what we will do when we will featurize this network. We will exploit these homophilic patterns into building very smart features that we can add to our tabular or Excel data set before we do the decision tree, logistic regression, or ensemble analysis. Um, if you look at these two networks, for example, to the left you have one network and to the right you have one network, and the green nodes represent legitimate customers. The blue nodes represent fraudulent customers, let's say. Um, where do you see what network is more homophilic, that one to the left or that one to the right? If I would just ask you to visually look at that, what you would hopefully say, I hope you paid attention to what I was saying, is you would see that there's more homophily in the network to the right, Because what does homophily imply? Homophily imply that the green ones are highly interconnected, and there's only loose connections between green and blue. So here you can see between green and blue, there's only two connections. Here you can see between green and blue, there's a connection here between green and blue, connection here between green and blue, connection here between green and blue, here, here, and here. So homophily means that the greens are highly interconnected, the blues are highly interconnected, and between them, there's only sparse or very limited connections. That's the base idea of homophily. You can write it down in statistical terms that are then going to look at dyadicity and heterophilicity. I don't have time to discuss on this, but if you'll be interested, I'm more than happy to give you some further um, background on this. And once we have this homophilic patterns in the data, we can start leveraging it. We can start using it to do social network-based predictive analytics. We can start using it to intelligently craft network-based features, which we append to our classical data sets and use that for building our predictive logistic regression, decision tree models, and so on. And how are we going to do that? Well, we're going to do that by making use of various types of things, right? Think about, let's again take the example of the telco setting, where you're being subscribed to a telco service, and you want to predict if customers are going to churn, yes or not. Well, if you want to predict churn in a telco setting, you can first of all look at the non-network information. Non-network information is the traditional information that we've been using, like a person's sociodemographic status, a person's address maybe. Address could also be valuable information. A person's marital status, a person's employment status if you have access to it. This is what we call non-relational information. Typical local customers information like Bart's age, Bart's marital status, Bart's employment status, Bart's income is not network information. So that information still remains very important. But on top of that information, I'm now going to use relational or network information. Now on top of Bart's local non-network information, I will also look at, has Bart any friends that he calls that recently churned? Right? When did they churn, etc. If many of Bart's friends churned in Bart's network, it may infect Bart to churn as well. So the components of social network-based predictive analytics are that we're going to use local classifiers, local models that make use of that local customer-specific information, but then also relational or network-based information. So the network is being featurized, is being added as separate features on top of the existing data. Collective inference is then a third component of any social network-based predictive analytics setting, and I don't have much time to elaborate on it for much, but basically what it does is it looks at the network dynamics, because I can influence Yvonne, Yvonne can influence Tom, Tom can influence Sarah, and Sarah can influence me back again. So the network is like a dynamic phenomenon where we mutually influence one another. That's what we call collective inferencing, right? So that's a third component for which we can do some analytical modeling. And one of the techniques there that we have used in the past, for example, is the Google PageRank algorithm. The Google PageRank algorithm is a very nice example of a collective inferencing procedure, as it nicely indicates the importance of a web page based upon the incoming links it has from other important web pages. So in other words, it indicates the importance of a node based upon the incoming references or influence of other nodes. Here you can see one example of coming up with a feature, and that's just applying a simple relational neighbor classifier. Here you can see the mathematics sounds a little bit complex, but if you go to the example, it's a lot simpler to explain, because here you can see the question mark is the node that for which you want to calculate a fraud probability, and it's connected to 2 fraudsters and 3 non-fraudsters. So the probability that this question mark is fraudulent, if you only look at the network, then you would have to say it's 3 out of 5, because 3 of the neighbors are fraudulent and 2 of the neighbors are non-fraudulent. So that's a feature that we can add to this node. So next to this node's age, marital status, income, we can now also look at the fraction of fraudsters in the network around the node and the fraction of non-fraudsters in the network around the node, which is obviously one is the complement of the other, but that could be an additional feature that you add to your data set. Or I can look at the probabilities. Here, instead of looking at the labels fraud or not, I can look at the probabilities of the neighboring nodes of that question mark to see which ones are fraudulent, which ones are non-fraudulent. I can factor in the probabilities, and then you would see that the probability that this node is fraudulent is 0.45 and hence non-fraudulent is 0.55. These are again two features that you can add to your data set and then do logistic regression on it. So these are two features, right? I can come up with more features, right? And the thing with social networks is that you have to be really creative when you come up with those features, right? And students or data scientists, especially data scientist students, they should excel in creativity, right? That's one of the core competences that I think you should acquire by taking all the data science courses that you're taking and the program that you're taking right now. So here you have this node part. This is the center node. The age was 44. Unfortunately, this is no longer correct, but anyway, let's assume it's 44. The income is 1000, and it has some other non-network characteristics. And now we add more network features, features that we have derived from this network. The modeling feature tells me what is the most frequent class in the direct neighborhood. The most frequent class is non-fraudulent. How many non-fraudsters do I have? 3. How many fraudsters do I have in the neighborhood? 2. Binary indicators. Do I have no fraudsters in the neighborhood? Do I have non-fraudsters in the neighborhood? So these are all network features that we append to our data set, and obviously they are correlated, right? If the frequency of no fraud is bigger than the frequency of fraud, then this will be no fraud right here, right? That's pretty obvious. So there's correlation between these features, but that's not a concern because any statistical technique like logistic regression, decision trees, random forest, ensemble methods, they can deal with correlation. That's not our main challenge right now. Our main challenge right now is to do the feature engineering, is to carefully craft the features that we're going to use for predictive analytics. How much time do I have left, Yvonne, to conclude before we have the questions?
5 minutes.
5 minutes, okay. Then that's actually something that I have more. That's something I will try to conclude with. I'll briefly go through the remaining slides, give you the gist of the slides. If you want more information, you can ask me. So the key secret and challenge in social network analytics is define a network, define the nodes, define the edges, and then featurize it into columns or predictors in your data set. I didn't have time to talk about bipartite graphs because right now we only looked at networks where we only had one type of node. The node was a person, a company, maybe even an email, a bank account, but you can look at networks where you also have multiple different types of nodes, which is what we did in our research. I had one PhD student that worked at bipartite networks, for example, where we had nodes that were companies and diamonds that represent resources. And the resources could be employees that are being shared between companies or employees that have moved from one company to another. The resource or the diamond could also be a physical address. That means that two companies are located on the same physical address, which could be something suspicious, right? So bipartite networks look at more than one type of node. They look at two types of nodes, right? Multipartite networks look at different types of nodes. They look at persons, they look at companies, they look at transactions, they look at addresses. Obviously, the more different types of nodes you include in your network, the richer the information, but the harder it becomes to featurize it. That's the key challenge. We have some very interesting research, in case you're interested, that was conducted by a colleague of a colleague PhD student of mine, Veronique van Vlesselaar, where we used this very idea of network-based fraud detection for social security fraud that was published in a management science paper, in case you're interested. So what are the conclusions, what are the key takeaways that I want you to remember from this very short talk on social networks for fraud analytics is that social networks are more than Facebook or LinkedIn or Twitter. You can think of any type of business application or settings where you have nodes that could represent people in a particular role. They could represent customers. Um, they could represent callers, callees. They can represent authors, etc. And you have edges that connect the people in a certain way. We zoomed into the basic concept of social networks and illustrated how they could be represented using adjacency matrix, adjacency lists. We discussed centrality measures as key descriptive statistical measurements of nodes in a network, like the degree, the closeness, the betweenness. We looked at community mining and the very important role that the betweenness was playing in the community mining. We looked at homophily, and if there's one thing that I would like you to remember, it's the sentence, birds of a feather flock together. That's what homophily represents. If there's homophily in your network, there's opportunity for doing predictive analytics, because then we can take the network and featurize it. And I've discussed very briefly various ways to featurize the network by looking at the characteristics of the immediate neighborhood, like how many fraudsters we have in the neighborhood, how many was the probability of them being fraudulent, etc. There's a lot more creative and more sophisticated ways of featurizing networks, which we didn't cover, looking at bipartite networks, multipartite networks, and even looking at collective inference procedures like Google PageRank, right? Google PageRank is going to indicate how one node is being influenced by its neighboring nodes due to the incoming edges, etc. We didn't have time to discuss upon that, but if you're interested, I'm very happy to refer you to this very exciting book on fraud analytics, which I've co-authored with two of my colleagues. I think I can wrap it up here, and I'm more than happy to take some questions.
Right. Thanks, Bart. So I'm going to stop the recording here so we can do the question and answer. Okay.